sound better?
Yes.
Great. All right, so here's a rough outline of my talk. I think I started at 9:20, but it does not mean I have to stop at 10:20. All right. So the first section, I want to introduce flat surfaces. When I say a surface, I mean a Riemann surface. Okay. So the best way to introduce a flat surface is to give you some examples. So let's start from the following. I want to take several vectors in the Euclidean plane and add them up. So suppose let's take v1, v2, v3, v4. So these are just 4 vectors in the Euclidean plane. Some color chalk here. So suppose I start from v1. Then I add v2. Then v3. Then v4. Now I want to write down an amazing equality. So this equals v4 plus v3 plus v2 plus v1. Well, it's non-trivial, but it's true. So let's just add v4 first, starting from the same initial point. So v4 is here. v3, v2. It's getting easier. So the last one is easy to draw because, well, v1. I need v2 here. All right. So those vectors enclose a planar region. And that is a flat surface after you identifying edges with the same labeling. In other words, you identify v1 with v1 here by affine translation. Okay. So you can check after gluing, this gives you a Riemann surface of genus 2 by using, say, Euler characteristics. There are only, after gluing, all the vertices become the same point P. So there is one vertex, 4 edges, and 1 face. You can check genus is 2. And you see the flat structure just indulged from the Euclidean plane using the standard XY coordinate. And away from the point P, so if you take two charts, see here, and the transition function is just given by translation. Right? Suppose here is Z prime, here is Z. So Z prime is just Z plus a constant. So transition functions are affine translation away from P. So at this point P, if you count the total cone angle at P, you can see the angle around P equals 6 pi. I'll write down another amazing equality. 6 pi is 3 times 2 pi. I'll use it later. Okay. But at least I think I convinced you this is a flat structure away from P. Everything looks like the Euclidean plane. And at P, you get more angle. Because usually you should get 2 pi. But only at P, it looks like a cone point, like a saddle point. But it's still a smooth point on the Riemann surface, but not smooth for the flat metric. Okay, because the total angle is not 2 pi. The multiple of 2 pi. All right. So if you look at the transition function, suppose we differentiate. So this flat structure actually induces dz. That is a well-defined global holomorphic one form on the Riemann surface. Let's call the surface S. Because it differentiates, the constant goes away. So it's a well-defined global holomorphic one form. And where is 0? Well, you can check only at this compound P, this one form has a 0. And what is the Vanchian order? That's why I wrote down this equality, because it's a 3 times 2 pi. The Vanchian order at that of this one form at P is 3 minus 1 is 2, because basically you're differentiating C to the third with a unique 0 at P of order 3 minus 1 is 2. You can also check, because genus 2g minus 2 is 2, so that should be the degree of the canonical lamp bundle. So everything is consistent. So conversely, suppose now we are given a holomorphic one form. I claim you can recover the flex structure on the Riemann surface. So let's just take some one form, omega be some holomorphic one form on a genus G Riemann surface. Let's fix the type of zeros of omega. Suppose omega has k distinct zeros at P1 up to Pk. Each Pi has Vanchian order Mi. And the total sum of those Mi should be equal to the degree of the canonical lamp bundle, which is 2g minus 2. Okay? That's my setting. We take some one form of a special 0 type, like that. Okay. So Mi's are positive integers, Pi are distinct. Okay? Then I claim this omega induces the flex structure on S. And how do you see it? I mean, roughly speaking, you take 2 points adjacent to each other, you take a path connecting them. You just integrate omega. That defines the distance between the 2 points. For instance, if you want to get a planar model like that, so how do we find those vectors Vi? You can do the following. You take a basis of the homology of the Riemann surface, punctured at the zeros P1 up to Pk. Okay. Without puncture, there should be like 2G bases for the homology H1, but there are like K punctures. You have to add K minus 1 additional bases. So the first 2G is just the standard basis of the homology H1S without punctures. This additional one, say gamma I, for I bigger than 2G is the following. So you can just take a path connecting Pi to Pi plus 1 for I is 2G. So let's do this, 2G plus I from 1 to K minus 1. Okay. And then you just define those Vi to be the integration of omega along those paths. Maybe Vj. Okay. And then you also see those vectors. Cut it out, you have this plane polygon model for a Riemann surface with the flat structure. Okay.
What is the shape of the boundary in general?
What is that?
What would be the shape of the boundary in general?
What do you mean the shape?
It would be these edges will not intersect themselves?
Well, you can arrange it in that way. If they intersect, maybe you just cut it open and reglue. Yeah, I mean, topologically, you can always do that, but now you have more structure. Any other questions? Okay, so how about these zeros of omega? So you can check if you do that. So this flat structure, it will have, just as in that picture, it has exactly k, I call it cone points. So where the total angle is not 2 pi, but a multiple of 2 pi, as those zeros, P1 up to Pk. And around Pi, the angle equals, because it's a 0 of order mi. That means you have to take Ci to the mi plus 1, differentiate that to get your one form. So the total angle is 2 pi times mi plus 1. Okay. Just as in the example I drew there. So you get a unique 0 of total angle 6 pi, 3 equals 2 plus 1. But that's a general thing. All right, I hope I have already convinced you. I mean, this is a two-way relation. Like flat structures or flat surfaces and holomorphic one forms basically the same thing, but like two different viewpoints. All right. Okay. Oh, by the way, I think this picture also reminds me of a joke Rahul told us at Joe's birthday conference. I think when Rahul graduated, once he came back to visit Joe, and he started drawing a curve like this. Usually, that's not what we expect, right? We want to draw a curve like that. But then Joe looked at Rahul, saying, Rahul, you must be hanging out with the wrong group of people. But today, I drawn the curve like that. I guess the group of people I've been hanging out with must be even worse. But anyway, their names will appear later in the talk, you will see. I can assure you it's not one of you. All right, that's the content of the first section, so let's move on. So I want to introduce Teichmüller curves. Where do Teichmüller curves live? They live in the so-called modular space of those one forms. So we want to study objects moving in a family. So here, suppose we want to study flat surfaces. Alternatively, we can just study one forms. But from this picture, you see, just in the plane, if you deform the polygon a little bit, it doesn't change the type of zeros, right? It only changes the shape. So in other words, if you want to study in the family, you should first specify the type of zeros given by those coefficients mi. So fix that, consider the corresponding modular space of one forms of flat surfaces. So that's the setting. So we take a signature called mu, given by k positive integers, unordered, okay, without order, a partition of 2g minus 2. Their sum equals 2g minus 2. So these are positive integers. Their sum equals 2g minus 2. I consider the following moduli space. I call it H mu. Parameterizing a pair, a Riemann surface of genus GS, along with a holomorphic one form omega on it. So S is of genus G, omega a holomorphic one form. In addition, I require the type of zeros of omega is determined by the signature mu. In other words, omega has 0 loci at k points, and their Wunsch orders are those mi's. Okay. And this is not a very strange object, even to algebraic geometers. I think many of you are familiar with it. If I take the union of all the, I call it a strata of differential, okay, or strata of one forms. Okay, so why do I call it strata? Because if you take the union of all of them for all possible mu, the union gives you the Hodge bundle, parameterizing all possible holomorphic one forms over Mg, the modular space of curves. So this map just forgets the one form, only keeps the Riemann surface, and you map down to Mg. Right. So that gives you a natural stratification of the total Hodge bundle. Right. So Teichmüller curves live in those strata H mu. So yeah, I mean, you can use well, I mean, I only consider smooth Riemann surface, but here, like those Vi I defined for you actually gives you a local coordinate of this strata for each strata. Particularly, it has dimension given by, complex dimension given by 2G plus K minus 1, given by those VIs, okay? So because their plane polygon models live in the Euclidean plane, you can take a, say, take a GL2 action by changing the shape of the polygon. So that naturally acts, that action naturally acts on the Hodge bundle and preserves each stratum because it does not change the type of zeros. And there is a GL2 action on each stratum H mu, just basically by changing the shape of the polygons. Or the flat structures, the flat surfaces. Okay. No, I mean the one form actually determines the complex structure, right? I'm saying it gives you more than complex structure.
But when you mod out, you don't mod out by this GL2R.
No, I just consider the action. I haven't really said anything about. I just say there is a natural GL2 action acting on the space, okay? Just by changing the flat surface. Okay. All right, so suppose you start from a general point, some random point in the Hodge bundle, look at the orbit, say project down to mg. The orbit closure usually is a total space, like the orbit goes ergodically around the total space, it takes closure, you get everything. But occasionally, if you start from a special point, some special one form, and look at its orbit closure project to mg, that orbit closure actually gives you an algebraic curve. That's a very special case, but it happens. If that happens, we just call it a Teichmüller curve. So if an orbit closure, I guess project under F, so F is a forgettable map there, is a algebraic curve, then we see that it's a Teichmüller curve. That's the definition. Okay. It's a very rare phenomenon. Usually we don't expect that. Okay, so the definition looks very abstract. So the first question is to ask, so do they exist? So what kind of Teichmüller curves we get? So let me just show you some examples, actually arising from a special construction using branch cover. So they do exist, actually there exist infinite many of them. Well, you are asking about the stabilizer?
The generic point.
Well, it should at least contains S, or suppose mod scalar, right? Then it certainly contains SO2R. It could contain a little bit more if it's special. Right?
No, the stabilizer. The orbit is an SL2R.
It will SL2R mod something.
Oh, more
Yeah,
moduli.
mod like further stabilizers.
I mean, are you getting something like the Ziegler space or?
Yeah, mod further stuff. It could be like some more like stabilizers, right? If you think of the genus 1 case, you have to use upper half plane mod gamma. Right. But anyway, why don't I give you some examples to make it more concrete? Let's just consider the following like Hurwitz curve. are denoted by TD mu. So which parameterizes a branch cover pi from some genus G Riemann surface S to a torus or elliptic curve. So this is genus G, this is genus 1. And the degree of the branch cover is of some fixed number D. And further require, there's a unique branch point, say sitting at the origin of E. And over this unique branch point, there should be several ramification points. But it requires the ramification points are determined by this partition mu. I'll make it clear later. I just simply say of ramification type given by mu. So this is a complex one-dimensional Hurwitz curve or Hurwitz space. Okay, so let me explain. So first, I consider those branch covers from genus G Riemann surface to an elliptic curve of degree D. So the covering curve has genus G. There's a unique branch point in E. Okay, and over this branch point, there are like many pre-image. But among the pre-image points, there should be k of them. And each of the point is a ramification point with ramification order given by those mi. And if you plug everything in the Riemann-Hurwitz formula, it works. Because the sum of the ramification order is exactly 2g minus 2. And the target curve is elliptic curve. Okay. And I consider all of them. So why is it complex one dimension? Because you have nothing to vary except the complex structure of the elliptic curve by the J invariant. So you naturally get a one-dimensional Hurwitz curve. Okay? So that's something, well, at least well known in algebraic geometry. So why does it have something to do with Teichmüller curves? So you can pull back one form from the torus, and that gives you one form living in the right stratum H mu. Say if you pull back one form from the standard torus, let's do pi pull back dz. So along with the covering Riemann surface, under this ramification type, that exactly give you a one form of the right type of zeros determined by mu. So this lives in the stratum H mu. Okay? And why is it an orbit? Well, at least an orbit projection. If you think about it, let me give you a concrete example of this branch cover. Let me draw it here. Let's take degree equals to 5, genus equals 2, and mu is a partition of 2g minus 2 in this case. Let's just take a single zero of order 2. I can draw the branch cover, and you see the covering surface has a natural flat structure. Suppose here's my standard torus E. Oh, that's too big. Oh, it's okay. So I want to take 5 copies of E and glue them together to form a branch cover. So I can do it as follows. One, two, three, four, 5. This is 5 to 1. And I want to identify the following edges. So first, this is an octagon with 8 vertices. So identify these 2 edges under parallel translation, and these 2, and these 2. And finally, I identify the 2 long edges. And this basically topologically is the same as the first picture I drew there. It's genus 2. And all the vertices will be identified as the same point. And if you count the total angle around that point, you still get 6 pi, which is 3 times 2 pi. So that corresponds to a 0 of one form of branch order 2, which is exactly in this setting. So that gives you a branch cover, and you see this flat structure. And if you apply this GL2 action on it, basically, you are really doing the following. You change the shape of this torus first by changing it like that. And then this also varies, just naturally. So if you do consider all possible elliptic curve or tori in this Hurwitz space, you basically recover everything by using this GL2 action. So this is naturally an invariant orbit. Okay, so that is an example of a special Teichmüller curve. And there are infinitely many of them because we can raise the degree d. There's no restriction on the degree. If you plug in Riemann Hurwitz, d can go to infinity. There's no bound. So you get infinitely many such Hurwitz type Teichmüller curves. Yeah, go ahead.
There's a bijection between the GL2R orbits and these.
No, these are like a subset. These give you very special Teichmüller curves. That's a good point. Maybe I should say. Where is my Hurwitz space? Okay, here. So the conclusion is this TD mu is an example, is a very special Teichmüller curve. Yeah, go ahead.
Where is this living in H mu or
in H mu, but I can project further down to mg because that's eventually what I want to do.
So I was wondering if this, I mean, is some sort of Shimura curve at the level of if you go to Ag, or because you are taking some sort of SL2, so you are taking the period and you are taking.
Yeah, I mean, I don't know much about Shimura curve, but I think they live in Ag. Well, today I don't want to get into that. Yeah, but this just live in the Hodge-bound. Okay. All right, so I said it's a special type of Teichmüller curves. So there are like other Teichmüller curves which do not arise from this branch cover construction. Actually, it's a mysterious. It's quite mysterious. We don't quite know how to classify all Teichmüller curves, even in low genus, genus 2, genus 3. It's a wide open question. Okay. All right. Okay, so I want to associate two numbers to every Teichmüller curve. The first number is called the Zygarewicz number. The second one is called slope. Okay. So they arise from different contexts. So let's start with the Zygarewicz number. I'll simply write it as V for short. Okay, so let's fix a torus. Say it takes a standard one, it's like that, unit square. Okay. Okay. Now, if you look at all possible branch covers over the fixed torus, suppose the branch point is at the origin, then there exist finite many such covers up to isomorphism. The number of such covers actually is called Hurwitz number. There is a very elementary combinatorial way to describe how to count Hurwitz number. But if you really count it, I mean, that combinatorial gets messy and messy. So anyway, so fixed torus E, so there exist finite many, let me just call the Hurwitz number given by n, respect to the degree and the partition mu, that is ramification type, different branch covers in that orbit or in that Hurwitz curve, TD mu over the fixed elliptic curve E. Oh, by the way, I think, I mean, just for the purpose of this talk, I will introduce the Zygarewicz number only using the special type of Teichmüller curves. I mean, you can define it in general, but I mean, if you just consider this Hurwitz type Teichmüller curve, you don't lose much. Actually, the definition is easier to define. So I'll just, for this section, I'll just restrict to the case TD mu and define the number for you. But it really works for general Teichmüller curves. All right, so let's label them, say pi 1, pi 2, up to pi n. So there are n different covers sitting over the fixed elliptic curve. And for each branch cover, I want to assign it a number, basically measuring the behavior of certain trajectory in their plane polygon model. You have a plane polygon. Sometimes you want to play billiards in the polygon and study the trajectory of the billiard. So I want to define number to measure this behavior. That's called the Ziegler number. So a sum, let me use another board. For each pi I, I want to assign number, call it W pi I, given by the following. It equals the sum of modulus or explained version of horizontal cylinders in that covering surface corresponding to pi I. Okay, so there are several terms I have to explain. So what do I mean by a horizontal cylinder? And then what is the modulus of a cylinder? Okay. So once I define these two, you can just take a sum of them. So again, let's just use this example. Okay, this is a perfect branch covers for this ramification type. Okay, so here is the covering surface. I look at the horizontal direction. Because these two edges, now they are glued together, if you consider horizontal trajectories, so those horizontal trajectories actually fill in two different cylinders on the surface. You see two of them. The top one, because these two edges are identified, this horizontal line just fill in a cylinder like that. And if you move to the bottom, these two edges are identified. And you get a different class of horizontal trajectories. And in particular, these two cylinders they filled in have different dimensions. So the top one has height 1 and also length 1. And the bottom one has height 1 but length 4. Okay? When I see them, so these are horizontal cylinders. What is the modulus? The modulus is given by the height over length. For each cylinder, you take its height divided by its length. So that's what I call the modulus of a cylinder. So in this example, we have two cylinders. So we take the sum of their moduli. So in this case, the sum of W pi equals 1 over 1, that is the modulus of the top cylinder, plus 1 over 4, the bottom one. That is the assignment for each branch cover pi I. Now I do it for all the n branch covers, and I sum up. Because that gives me the total number of modulus of all horizontal cylinders lying in the n branch cover surface. And d mu is the sum of those assignments, W pi I, for I varies from 1 to n. Okay? And there are several questions maybe you want to ask me. So first of all, why don't I only pick horizontal direction? If you change your direction, goes vertically or along diagonal, it seems you get different cylinders at different height and length. And the issue is, I guess the point is, I didn't really claim this is well-defined. But once you take the sum, it's well-defined, because you are in an orbit. If you change your direction, as long as you do it uniformly for all the n branch cover, so this assignment, this number will go to another branch cover if you change your direction. Because basically, there's no standard way to. So here I just pick this alpha beta as a standard basis for the homology of E. But if you change the shape of E or change your choice of basis, basically upstairs you change it uniformly, so the sum is always well defined. Yeah, because it's an orbit.
You didn't say what is the trajectory.
I didn't say what is the trajectory.
Yes.
You know, that is a geodesic which does not hit the cone point of your flex structure. Okay. But you see, if you go up from here to here, you necessarily have to pass the cone point. So these are interiors are filled in by those horizontal trajectories. Does that answer your question? Okay, another issue is that why do I consider this very strange, like moduli of cylinders? Why don't I just count 2? Well, basically, I mean, there's a reason. It will become clear later, but in algebraic geometry, when you do intersection theory, counting intersection numbers, sometimes you see one intersection point, but you count it as 2 or 1/2 because of the intersection multiplicity. Here is the same idea. You really want to count it with certain parameters, some information of the cylinder. So that is one natural choice is given by this. Okay. Right. Anyway, so this, I guess, is not really defined in the context of algebraic geometry. But anyway, so let's finish the definition of zig of H. So I have this total sum of moduli of cylinders given by M, and I also have the Hurwitz number n. So let's take the quotient m over n. So that is the definition of the zig of H number. Now I just define the zig of H number for the Teichmüller curve. I use little c to denote this zig of H number, just given by the quotient m over n. I mean, as I said, you can really define it for arbitrary Teichmüller curve. But in this special case, actually, there is a purely combinatorial description. So this is a Hurwitz number. You can just, for low degree genus, you can really count it by hand using the symmetric group acting on the D letters, satisfying certain monodromy conditions. And for the top number, for the numerator, well, if you can write down the n-branch cover like that, you see the cylinders, you can just count. So this is, in some sense, like just combinatorial description. It's a very discrete way to define zig of H number for the special type of Teichmüller curve. But in general, so this number just measures the behavior of those trajectories in the orbit. Okay. All right. So let's move to the next concept we are more familiar with. That is slope. That is easy to define because most of you know it. So I take this map from the Teichmüller curve, say any Teichmüller curve T, to mg. Okay, just by forgetting the one form, only keeping the Riemann surface. And that gives you a complex one-dimensional family of genus G curves. Okay. And now suppose we take the closure using the Deligne-Mumford compactification, including the boundary of nodal curve. And then, at some point, the closure of this Teichmüller curve might just hit the boundary of mg bar. I mean, in that case, you just consider degenerate branch covers using the emissive cover. So there are several divisor classes we can use on mg bar to study the intersection of their class with the Teichmüller curve. So on mg bar, I want to use delta to denote the total boundary of nodal curves. Okay, that is a divisor. And I define another divisor class, lambda, that is the first chain class of the Hodge bundle. Or the determinant of the Hodge bundle is a lambda bundle. Now I want to take their degrees, restrict to the Teichmüller curve, and divided one by the other. That quotient, I call it slope. I use little s to denote the slope associated to a Teichmüller curve, just given by the degree of the delta class on T divided by the degree of the lambda class on T. These are numbers. You can take the quotient that give you another number, which is slope. Okay, so here's a chance I can redeem myself. Let me get back to this familiar picture. Suppose this is actually any one-dimensional family of genus G curves. Okay, so now let's draw a curve like that. Okay. So this is a universal curve sitting over the one-dimensional curve, okay, one-dimensional family. So from the setting of the numerator, you can see, roughly speaking, it really counts the number of nodes in this family. Right? So that's the definition of delta. For the denominator, lambda basically tells you how the modular structure varies in this family. And if you take the quotient, so this number indicates how the moduli vary respect to the number of singularities in this family. So it's definitely the most important index you can associate to a complete one-dimensional family of genus G curves. All right. Okay, so I spent a lot of time setting up these two numbers. They arise from different contexts. One is defined by using billiard in polygon or some combinatorial description, and the other one is defined by using the intersection on modular space. So they seem unrelated, but indeed, they are very closely related because they determine each other. So here's a theorem. So again, so let's take this mu as a partition of 2t minus 2. And let's define number purely depending or determined by mu. I call it kappa mu. It's some constant determined by mu. Okay, it looks strange, but it just arises from computation. Once you fix the signature mu, this is just some number. Okay, only depends on mu. All right, then I have a formula to represent Ziegler-Witch and slope. For any Teichmüller curve in the stratum H mu, so their slope is slope, and Ziegler-Witch satisfies the following relation. The slope equals, let's call it Teichmüller curve T. So ST equals 12 times the Ziegler-Witch divided by C plus kappa. And as you can see, once you know the slope, you know the Ziegler-Witch number, and vice versa. So they determine each other. So I proved this formula for the case of Hurwitz type Teichmüller curves, those TD mu. And recently, with my collaborator, we just quickly extended to arbitrary Teichmüller curves. The idea basically is the same. That is Martin Moeller in Frankfurt. Okay. I can't really get into the detail of the proof, but if you are familiar with the Grothendieck-Riemann rock applying to the universal curve over the Teichmüller curve, you immediately recognize what is the hidden ingredients behind this formula. Yeah, it's not that different from the, I guess, the Mumford relation or Noether formula. In any case, let me just give you one idea how to make the connection between these two, because they look unrelated. So basically, let's get back to this picture. So the numerator of the slope given by the intersection with boundary. In other words, you have to enumerate the nodes arising from the degenerate branch covers in this special case. Okay, and how do you degenerate a branch cover? Well, I mean, degenerate with this torus. So this eventually becomes a one-nodal Riemann sphere or rational one-nodal curve in M11 bar. Right? So this degenerates to something like this. Failed again. Sorry for that. Okay, you have some vanishing cycle here, which shrinks to a node. You close the edges. Accordingly, you get a one-nodal Riemann sphere. That is a rational nodal curve, complex curve. Okay, and upstairs, the branch cover also degenerates by shrinking the pre-image of this vanishing cycle. Basically, you just shrink those trajectories to get something like that. And you also have to glue the edges in the right way to form a closed degenerate Riemann surface. But you do see singularities or nodes, they appear corresponding to degeneration of the horizontal trajectories. And if you want to count the right intersecting number with delta, that's corresponding to the modulus of each cylinder. So they do correspond to each other, at least for the numerator. So once you make this observation, the rest part of the calculation, well, again, if you know the Grothendieck Riemann rock, it works just like a charm. Any questions? Right. So the next question is to ask, how do these numbers look like? So we have a relation between them, but for some genus, some degree, or some partition mu, so we want to get a numerical data of the Ziegler-Witch slope. So that actually breaks to two cases. So in low genus, they have a very interesting behavior. I call it a non-varying Ziegler-Witch phenomenon. So let me explain. Okay, so first let me give you a quick definition. So let's take a stratum H mu. So for H mu, with a fixed partition of 2D minus mu. And consider all possible Teichmüller curves sitting inside H mu. I already told you there exist infinite many of them, at least by using the branch cover construct. But there could be more. But there are infinite many of them, H mu. For H mu, if all Teichmüller curves in this stratum H mu, suppose they have the same Ziegler-Witch number. I mean, a priori, there's no reason why they all have the same Ziegler-Witch number, right? They define for each Teichmüller curve. They could vary a lot. But suppose this happens. Then I'll just say that this stratum is a non-varying stratum with respect to this Ziegler-Witch behavior. In short, I'll just call it a non-varying stratum. Well, it has this non-varying property. With respect to the Ziegler-Witch number of Teichmüller curves in this stratum. Okay. So as I said, there's no a priori reason this should happen, but it does happen in low genus at least. So that was a question posted by Kontsevich and Zorich about a decade ago. They had some computer program which can give you numerical data of those numbers. Because at least you see for the branch coverage case, this special type Hurwitz Teichmüller curve for small genus, small degree, you can write down by hand all the branch covers and enumerate these numbers, takes the quotient. And if you have a computer program, well, you can even get more data. But they found for many low genus stratum H mu, they take several Teichmüller curves in that stratum, all of them have the same Ziegler-Witch number. It's strange. So I learned this conjecture from Anton Zorich. I mean, I personally never hung out with Kontsevich, never met him. But I do know Anton. So let's just attribute to Kontsevich and Zorich. So roughly speaking, it says the following. So the following, so in low genus, the following stratum of orthogonal one forms have the non-varying behavior. I'll just quickly write down a non-varying, okay? So it's a concrete list consisting of maybe 10, 15 different strata. So let me not get into the detail, but just give you some examples. See, it's starting from genus 2, 2g minus 2 is 2. So there are only 2 possibilities for mu. Here's mu could be 2 or 1, 1. And both of them are non-varying in terms of that definition. And for genus 3, 2g minus 2 is 4. So you start from 4, you get 3, 1. You take all possible partitions of 4. All of them are OK, except the most general one, 1, 1, 1, 1. So in that case, you can have 2 different Teichmüller sitting in that strata that have different Zieger-Wicht numbers. So it is not varying. It is not non-varying. But away from that, all the others have this non-varying property. And the list just goes on. Genus 4, let me write maybe 6 and 5, 1. There are quite a lot. Roughly speaking, there are half of them, half of the mu in genus 4. Have this non-varying property. And genus 5, there are a couple of them, starting from 8 and 7, 1. And there are maybe 2 or 3, but there's several of them, not that many. And it seems to stop at genus 6, because at genus 6, even if you take the most degenerate stratum consisting of a unique zero given by 2 times 6 minus 2 is 10, even for this most special stratum, you see for all the other smaller genus, 2, 4, 6, and 8, they all have this non-varying property. At least your expectation is that it should hold. Suppose it holds for some stratum in genus 6 or higher, it should at least hold for 10. But 10 is varying. So it's only a heuristic observation. It seems this behavior stops at genus 6. It's only a low genus behavior. Anyway, so this now become.
Is it conjecture or observation?
Well, I mean, they made this observation 10 years ago, but Zorich formulated a conjecture, and I learned it from Zorich.
So what is the conjecture?
It's just this.
This is a complete list?
Yeah, I mean, they had a computer experiment which is quite efficient that cook up low genus Teichmüller curves that can give you all the data you want. You take several of them in the same strata, you observe that the Zieger-Wicht numbers are the same, then they just make this conjecture. And if you want to conclude one is varying, you just need to come up 2 Teichmüller curves in the same strata that have different Zieger-Wicht. I mean, if you have like 3 of them in the same strata, if they have the same Zieger-Wicht, you can almost certainly say, okay, that is a non-varying stratum. It's a very strong numerical, very efficient numerical program. Make sense?
To the point it's hard to check all of the Teichmüller curves in the strata, right?
You don't have to check, but if you check it, it just becomes a theorem. Again, that is a recent joint work with Martin Moeller. I mean, the proof actually is quite well. If you are algebraic geometer who randomly got into this question, it's not that hard to prove, because I have this formula right here. Once I want to verify, suppose we want to verify it's non-varying Zieger-Wicht. Alternatively, I can just show the slopes are non-varying. But that's what we know how to do. So I can't really give you the proof for all the strata. Let's just take one of them. For example, so let's just prove it for one case when genus is 3. And the partition mu is 2g minus 2 is 4. Let's take 3, 1. OK, so that is a partition of 4. And I want to show you in that case, at least you get non-varying slopes for all Teichmüller curves, then we are done. So let's take a flat surface in that stratum H31. So you have a genus 3 Riemann surface S along with a holomorphic 1 form omega. Okay, and suppose it sits in this stratum H31, and that tells you the 0 loci of omega consists of 3p1 plus p2. So it has 2 zeros of one chain order 3 and 1, respectively. p1, p2 are distinct. Yes. All right. So if this is a genus 3 curve, I mean, you may also realize that this is exactly a canonical divisor, right? So this is a section of the canonical line bundle of the Riemann surface. So you have a genus 3 curve admitting such a canonical divisor. So what can you conclude about this genus 3 curve? Oh, that's a question for you. Yeah, thank you, Joe. You suddenly realize it's not a hyperelliptic curve. So your conclusion is that S is not hyperelliptic. It's not hyperelliptic. Why is it? So hyperelliptic curve admits a 2-to-1 double cover to P1. There is a hyperelliptic involution. Suppose S was a hyperelliptic curve, the hyperelliptic involution would switch the zeros of the one form. But these two distinct zeros do not show up in conjugate pairs. They have different coefficients, not even coefficients. So that simply tells you S is not hyperelliptic. All right, this is very good because now we can look at the modular space of genus 3 curves and the locus of hyperelliptic curves. That forms the codimension 1 locus that is divisor in M3 bar. So we just consider let's H hype to denote the locus of genus 3 hyperelliptic curves in M3 bar. Then this tells you if you take a Teichmüller curve, it must be disjoint from this hyperelliptic locus. So, okay, then for any Teichmüller curve in this stratum, it's still denoted by T. And you may notice that here I did not use any other information about this Teichmüller curve. It could be an arbitrary one, as long as it lies in this stratum. Then by this kind of argument, you show that T and this hyperelliptic curve locus actually is a divisor. You can quickly check its codimension 1. So T dot this hyperelliptic divisor is 0. Their intersection number is 0 in M3 bar.
But I mean, your curve is not proper.
I take the closure in M3 bar. That's,
this condition still holds.
yeah, that's one of the most technical points. You have to check it along the boundary. So that is due to some special property of Teichmüller curve. But you can see it from the, yeah, from, yeah,
Sorry.
go ahead.
But I was saying, so here it might work, but I mean, this kind of argument, so your curve is open.
Well, I guess I should really change my notation. How about this? I just map it down to mg first, then closed up. That actually started when I define slope. Otherwise, slope is meaningless. I didn't change my notation, but you know, when we do intersection, we always close up mg to mg bar. Otherwise, yeah, that's a good point. Yeah. Starting from slope, yeah, I do consider Teichmüller curve mapping into mg, but then I close up. Take this image inside mg bar as some complex curves, then I closed up. For instance, in that special case, just consider degenerate branch carvers. That is admissible.
Yeah, I mean, my question was maybe rather, so is this kind of curve close to something like AG without the compactification and things like that?
That I'm not sure, but in MG, it always hits the boundary. There's no way for the Teichmüller curve in MG to be complete. Yeah, it's necessary to the boundary. I think that was proved by Howard Mazur or John Smaley. Yeah. Yeah.
Is there any way to count the intersections with delta naught, delta 1, and delta 2, and so on?
That's another good question I was trying to not tell you. It only, for this type of Teichmüller curve, it only intersects the first boundary, delta irreducible. It never hits the higher boundary, delta I. Because you can see it from this picture. I mean, here, I only use this special example, but you get a sense. So this node has two preimages here by shrinking to vanishing, like the preimage of the vanishing cycle. But in the branch covering surface, So if you look at topologically, these two vanishing cycles, they are non-zero in each one. Otherwise, their image will be 0 in each one 0, but it's not. That tells you if you shrink them, that always gives you non-separating nodes, which only lie in delta naught. Another, if you remove the nodes, the total curve remains connected. It does not hit higher boundary. That's a good point, because now I have used a class of hyperlip curves. It does have higher boundary, but I don't worry, because I just explained it only intersects delta naught. So more higher boundary.
Isn't that argument, though, only for these Hurwitz Teichmüller curves?
Yeah, but because I never really defined the Ziegler-Witch for arbitrary Teichmüller curve, but it holds for arbitrary Teichmüller curve. Yeah. By the similar idea, but you have to revise the argument a little bit. Work with this GL2 action, see how it contracts the core curve or cylinder. But after you remove the nodes, the resulting node, you can check it's always connected to the total curve. All right. Okay, then we can finish this proof quickly. In this case, you can, well, this is an exercise just in module of curves. So that is the divisor class of the hyperlip curve in M3 bar. Okay, but I also told you a Teichmüller curve T does not hit higher boundary. I didn't quite prove, but you got the idea. In other words, the only intersection with boundary comes from these irreducible nodes. Then that tells you, by using this zero intersection, well, I guess I erase it. So T dot hype is 0 tells you if you plug in the slope as T, the definition is given by T dot delta or delta naught over T dot lambda, that is none. So you just got a non-varying slope. And you go back to the formula, so you can conclude for all the Ziegler-Witch numbers of such Teichmüller curve in that stratum, they are also non-varying. So that's finished the proof. So in general, this idea just applies for all the other cases. But the divisors you use, sometimes they do not really live inside MG bar. You have to mark the zeros of the one form, lift it to the modular space with marked points, and using some generalized Brown-Noether type divisors. But again, you have to come up with a divisor you show is really disjoint from your Teichmüller curve, then you are done. Okay, I think my time is up, right? As you can see, I still have one section I didn't quite get into, but the good news is that I don't have much to see. Okay, so that is the content of large genus case. All I want to say is the following. Okay. All right, so that's it. Thank you.
Any questions?
Can you say anything like what do these Teichmüller curves look like in the charting? Are they tautological classes in the charting of MG?
In the charting of MG bar, that's your question? Yeah. Again, for low genus, you just get that, right? Because you figure out at least up to a scalar. You know the slope, then you know that ray spanned by all these Teichmüller curves. Another, you know the slope of the Teichmüller curves that determines the ray in the Maury cone of curves, right? Because that comes from the intersection with lambda and boundary. But suppose you don't know the slope, then you just don't know it. Yeah. That's why I put a question mark. In other words, for large genus, you lose this behavior, and it's unclear how this Ziegler-Witch number behave. Okay.
So have you been able to find any errors with especially low slope?
I mean, you see, usually for low genus modular space, I mean, those divisors of Brown-Noether type usually give you the smallest slope. Yeah, most of the time I use the Brown-Noether divisors. So if you have this disjointness, then that Teichmüller curve has, in some sense, like the same slope as the Brown-Noether divisor. So in terms of divisor, the slope is small. It's very small. Could be the lower bound of the slopes of all effective divisors on MG bar for small genus only.
What about Or you just don't know?
I don't know. I studied this question 3 or 4 years ago, totally from different perspective, but I didn't really resolve it because I was hoping to analyze the limit of this Hurwitz Teichmüller type curve about their limit of slopes as G and D approaching infinity, but we only had eventually some numerical data. It's not a rigorous proof.
Is there any work on these flat structures where you have like orbital point? If the cone angle is not a multiple of 2 pi, it's like a fractional multiple?
Oh, that's a very good question. So if you did look at the abstract of my talk, I actually said 2 types of flat surfaces. One is flat surface, the other one is very flat surface. I mean, today, although I wrote down flat surface all the time, I meant very flat surface. If for your question, suppose you have a cone angle of multiple of pi, not 2 pi, then you still get a flat structure, but your transition function cannot be only given by affine translation. You have to allow reflection, like z goes to negative z. That gives you some cone angle of multiple c pi, or some other rational multiple of pi, of 2 pi. But then the transition functions are not affine translation. Why don't I just quickly give you an example? So suppose you do something like this. Just take the surface of a cube. That is the flat surface of the Riemann sphere, right? But I mean, it's not that flat. Because the cone angle is not a multiple of 2 pi. So yeah, you can study those objects, but it's, I don't know. You can study it.
Check my understanding. It seems to me that diagonal space is actually lives in the projectivization of the whole function.
Yeah, you can mod everything by scalars. That's fine.
That's the only way it becomes a curve.
Because you see, when I see Teichmüller curve, I did it carefully. Right? I said the orbit closure under the projection to mg is an Algebraic curve. I did use it, parentheses under f. Yeah, so the projection is a complex curve. In that case, I call it Teichmüller. Otherwise, it will be definitely, as you said. You consider all possible scalars, you scale the one form, you still have the same Riemann surface, right?
But again, I'm rephrasing my question. So I mean, are you actually looking at mg or the image in AG?
For
your Teichmüller curve seems to be something like the upper half, the middle upper half, modulo, and arithmetic is the same. And sometimes those kind of curves.
well, I mean, I think your question certainly makes sense if you talk to my collaborator Martin Moeller. I think he sometimes studies Teichmüller curve and Schumacher curves living inside AG. But I'm not that person to ask. Yeah, for now, I only consider things in MG due to my limited knowledge.
All right, if there are no further questions, let's wait.